From this lecture, we start talking about part 3 of this class, which is FDM for parabolic equations. That's a first real PDE. In other words, we have either U is a function of both time and space. U is ut of t and x, and it satisfies the PDE, which is ut is equal to uxx on 0 and 1, which is, as we were saying at the very beginning of the class, it models, for example, the temperature distribution of the rod, and instead of steady state, here we are given an initial condition. So at time zero, it has at the first instant, it has some temperature distribution u0 of x is x. And we also have the boundary condition, which is u0t is equal to g0t, and u1t is equal to g1t. Alright, so the two ends, if g0t and g1t are constants, then the two ends of the rod are placed in an environment that has fixed temperature, for example. And then this equation models that this is a homogeneous rod, and this equation then models the temperature distribution as time goes by. Okay, as time goes by, this really should be xt. All right. So we are caring about how to solve them on computers. So we're going to talk about numerical schemes. This video is about the two basic schemes for discretizing that. So here the idea is that we continue with what we had before. Okay, for the steady state case, from 0 to 1 we have x0, x1, x2, all the way to xm plus 1. Now, as time goes by, we denote time at a second dimension. So as time goes by, we basically discretize the xt domain. So it's like instead of an interval, you have a square, you have a rectangle. Okay, and here is t equal to 0. And here is t equals the final time, capital T. Okay, capital T. And we are going to discretize the t interval 0 to t into smaller ones of size delta t. So here we have h, there we have delta t. Okay, so then by resolving t at the next time level, basically what we do is that we try to find approximations at those same grid points. Okay, and we go one more level. So t is equal to 2 delta t, and then dot all the way to t is equal to capital T. And we also resolve the function by calculating its values at those x points. Okay, so basically the exact solution, u is approximated by these guys u sub I sub n what that means is that this is approximation to u at xi tn. Okay, and so we have I is equal, is for x, xi 0 to n plus 1, n is from 0 to, let's say, n, capital N. Okay, with capital N is equal to capital T divided by delta T. So xi is equal to I times h, alright, with h is equal to 1 divided by n plus 1, and tn is n times delta t, okay, delta t. So what we do is that we need to discretize ut, and then we are also going to discretize uxx. Okay, so we from 361 we have a lot of schemes for discretizing ut. Okay, and here is a part 2, discretization of uxx is part 2 of the 362 that we just did, right? So basically we put those two things together, we have a scheme for the parabolic equation. The two basic schemes we're covering here, the first one is, the most straightforward is that we're going to do a forward Euler, okay, for a long time. So that's the d plus for u sub t. Which is, we're going to have the u I n plus 1 minus u I n divided by delta t. Alright, so this our ut is equal to u the uxx, which is what we just did, ui plus 1 minus 2 ui plus ui minus 1. This is divided by h squared. Of course, we're going to, what's different from the steady state is this time log n, time log n, time log n. Alright, again, this is like ut, that's like uxx. Okay? So that's a scheme. We can rewrite that as everything in terms of uim plus 1. So the idea is that you are given the initial condition, so you know the set of ui when n is 0, right? That's known as the initial condition. And use those, you can calculate ui1, the value of the function at the first level, okay, by the formula we just that we just provided, that scheme. And once you have ui1, you can calculate ui2s and so on and so forth, right? So we're going to rewrite this as uin. We can multiply both sides by delta t and then add uin to both sides. So we're going to have delta t over h squared ui plus 1n. For the uin, we have the 1 from the left hand side, so this is 1 minus 2 delta t over h squared uin, alright, plus again delta t over h squared ui minus 1n. Okay, so what this equation does, it facilitates this calculation, right? So the schematically, what this is that you have this, you have this, you have this, you have an xi, all right. This is time level n, and then the next level is time level n plus 1. Here is time. So we're going to calculate the value here by using the values from here, here, and here. Okay, that's exactly what we have over there. All right. By using the to the left and right neighbor, and then the point itself at the previous level, we can calculate the point value at the current level. Okay, that allows us to do the iteration that we just described. It give me UI zeros, the first initial condition. I can calculate UI ones, and given the newly calculated UI ones, I can calculate UI 2. You sort of sweep upward along time. Okay, you sweep from the initial condition all the way to the final time. So there's really nothing fancy about this scheme. We basically combine the two schemes that we have. We do need to do a little bit analysis. So the local truncation error analysis, the local truncation error. Here, instead of tau I, we have tau I n. All right, so you add the ith node and nth time level. What that is, again, is you plug in u, the exact solution u, into your u scheme. So we're going to have u xi tn plus 1, right? That's ui n plus 1, minus u xi tn divided by delta t minus the right hand side. Okay, what is right hand side? Right hand side is ui plus 1n, which is approximating uxi plus 1 tn minus 2 uxi tn plus uxi minus 1 tn. This whole thing divided by h squared. Okay, and this is this because the tau I n, what this is at xitn, right? So that's a starting point of our Taylor expansion. So which means when we do Taylor expansion, we should expand around Tn, okay? And then the next group expand around Xi. So what we have is that, well, that's just u xi tn, all right, minus ut xi tn times delta t, right? The tn plus 1 minus tn is delta t. Plus order delta t squared minus u xi tn. So that's this guy. Okay? Just Taylor expansion. We did it many times. This divided by delta t. Alright? The second term we did many times. We know that's just uxx. We just did in part 2. The uxx at xi tn, and we have from xi plus 1 we have h to the 4th over 24, have another h to the 4th over 24 from xi minus 1. That's what gave us the h squared over 12, because we're cancelling one h squared from with the bottom. So that's uxxxx at xi tn, and what's left, remember, is there's no odd term. The even term is odd a to the 4th. Okay, and if you simplify, you see that, well, the uxi tn cancel with the uxi tn, so we have delta t cancel with delta t. We have ut at xi tn, right, plus order delta t. The numerator is order delta t squared. You cancel with the delta t at the bottom, minus uxx at xi(tn) plus order h squared. And if you simplify this a little bit more, you'll see that this order delta t is delta t, the second time utt, and times delta t squared over 2. Alright, and so which means this whole thing is order delta t over 2, delta t squared over 2 cancel with 1 delta t from below, and the h squared is minus this minus sign, minus h squared over 12. Okay, so which means the local truncation error is first order in time and second order in space. In space, regarding h is h squared, so second order, but for time is first order. So a typical thing to do is that well, we forgot to mention these two. They because use the exact solution, so that's equal to 0. Okay, so ut minus uxx, this evaluated at xi(tn), that's just 0 because u is the exact solution. Okay, that's why we only have order delta t over 2 minus h squared over 12. So a typical thing to do is that because now there are two sources of error. Okay, there are two sources of error. One is error is from space, the other one is from time. So for example, if you want to measure the accuracy of the scheme in space, then you want to keep the time error as small as possible. So you want to use a much small delta t, and which allows you to visualize performance of the scheme when h changes. Or the other way around, when you want to evaluate the dependence of the scheme on delta t, then you want to keep your space error small. So that's basically the interplay of time error and space error. Okay. You just need to, when we solve parabolic equation, you just need to be aware that there are actually two sources of error instead of, for the steady state, that was just one case, one source of error. The second scheme is the so-called Crank-Nicholson. Remember what we did in 361 is that when we have the ODE, all right, so we have the u prime is equal to f of u. Okay, so what we did is that, well, all the schemes are starting from the integral. We have tn plus 1, all right, this is equal to tn plus the integral from tn to tn plus 1 of u prime, right, dt. So then solving this is about how do we integrate this numerically. If we take the so-called trapezoidal rule, we have the Crank-Nicholson scheme, which is this u tn plus delta t times what? 1/2 of fm plus 1 plus fn. Okay, so exactly the same thing is going on here. So we have u sub t is equal to uxx. Okay, so what we have is that we're going to have the u I n plus 1 is equal to u I n, all right, plus 1/2 delta t, okay, and the evaluation of the uxx at I n plus 1 plus uxx at I n. All right, so this is this guy, that is that guy, okay? This is the correspondence with what we did before. To see this is that we have, or we simply have the uin plus 1 minus uin divided by delta t. All right, that's ut, okay, is equal to 1/2. Ut is the uxx. We're going to do 2 uxx and then add together divided by 2. Well, the 2 is the uxx at in plus 1, and then you have uxx at in, right? So the average of this is approximating uxx. Okay, so that's h squared u I plus 1 n plus 1 minus 2 ui n plus 1 plus u I minus 1 n plus 1, alright, plus h squared u I plus 1 n minus 2 ui n plus u I minus 1 n. Alright, so 2 applications of what we just did for steady state and take the average. So if we write this in terms of like what we did of the first scheme of the unknowns, the equation values, the unknown values at n plus 1 is in terms of everything else, is in terms of the values at n, okay? We cannot really rewrite this in terms of ui n plus 1. What we have is you have a bunch of them, or we're going to move the n plus 1s to the left, okay? So if you move the n plus 1s to the left, and then move the n's to the right, we're going to multiply both sides by delta t, okay? So we have, if also we want to simplify things, we want to define r to be equal to delta t over 2h squared, okay? So we have uin plus 1 minus uin. Let's do it step by step. We multiply both sides by delta t. We have r, right, times ui plus 1 n plus 1 minus 2 ui n plus 1 plus ui minus 1 plus 1 plus ui plus 1 n minus 2 ui n plus ui minus 1 n. Okay, and then we move n plus 1s to the left and then move the n's to the right, and then combine similar terms. We easily see that we have negative r ui plus 1 n plus 1, right, plus 1 minus 2r, 1 plus 2r, ui n plus 1 minus r ui minus 1 plus 1. That's equal to, we have the r ui plus 1 n plus 1 minus 2r ui n, and then plus ui minus 1 n, okay? So this is not as easy as the last scheme. We can simply evaluate ui n plus 1. Here they are all coupled together, so we need to write them as a linear algebra system and then solve, okay? So if we denote un a big vector to be u1n all the way to umn. Okay, remember the x interval is x0, x1 all the way to xm plus 1. So these two n values we know. So what we don't know is from x1 to xm, right? So that's why it's u1 to um. And which we know, well, we also, that's that um plus 1 vector is this the u's at time level n plus 1. So what do we have is have a linear system. Okay, linear system. We have 1 plus 2r, alright, 1 plus 2r, that would hit with the ui's. This is, so here I is from 1, 2, all the way to m. When I is 1, okay, and when I is 2 and 3 and so on and so forth, each one gets equation. The same fashion as we did for the steady state. This is u1 m plus 1, u2 m plus 1, all the way to um m plus 1. Okay, so on the subdiagonal we're going to have minus r. Here is minus r. Okay, and what we have left is that we are going to have, when I is 1, we are going to have this I minus 1, right? So this guy is for the I, that guy is for the I plus 1, right? This guy is I plus 1s. So the I minus 1s on the subdiagonal, but when I is 1, we have I minus 1 is 0. So the same thing as we did in the steady state. There's a u0, there's a u0 and plus 1 term, right? That multiply with negative r, then move to the right hand side. We have the r g0 at tm plus 1. What that is that's a u0 m plus 1. Okay, that's what we moved to the right, and that's the only fig, and it's 0 in the middle. And now we have the last one, which is r g1 tm plus 1. Okay, these two things would take care of all the plus 1s. Now for the n's, right, the plus, the n's the same, say similarly. So we have the u1n all the way to umn. Alright, this time we have the 1 minus 2r hitting the i's. So 1 minus 2r for the main diagonal. And then we have, we lost r here. We have r hit the ui plus 1s. And then we have r hitting the ui minus 1s. Okay. So, and similarly, what we have is that we need to add this first and last term. When I is 1, we had the u0 n, right? So it's r g0 tn 0 0, and then r g1 tn. So again, this is our u0 n. That's our u m plus 1 n. That's a u m plus 1 m plus 1. Okay. Is this guy here, and then this guy here. So this then is pretty straightforward, because if we denote this matrix by A, that matrix by B, alright? So what we do is that we have the UA, A, U, M plus 1, right, is equal to b un plus two vectors added together, that becomes r g0 tn plus 1 plus r g0 tn 0, 0, and then we have r g1 tn plus 1 plus r g1 tn. Okay, so this means that the un we cannot write so as un plus 1 is in terms of something. We cannot do that now, but we can write this whole vector, not just one component. So vector, then if we multiply both sides by A inverse, it's A inverse times B, that's a matrix. This applies to un plus A inverse times this vector. R G0 Tn plus 1 plus R G0 Tn 0, 0, R G0 G1 Tn plus 1 plus R G1 Tn. Okay? So numerically, we discretize x and t, right? Then you can compute r, which is delta t over 2h squared, right? Discretize x and t. Here we get x, then we get delta t, and then we form a and b and a inverse b, right? And then we can advance in time given, which is i.e. solve for un plus 1 given un. That is a process when n is 0, 1, 2, and so on and so forth, all the way to capital N. No U0, you calculate U1. No U1, you calculate U2, and so on and so forth.